Okay, so we're going to start here today. Thank you guys for your patience. We're in Mibnei HaMachshev, Computer Architecture, Chapter 2. Well, we're actually Chapter 3 now. Let me do View Present. Okay, is that better? Oh, not yet. Oh, I don't know if this present is going to work. Okay, forget about present. You can see fine? You can see my screen fine?
Yeah.
Yeah, okay. So, wait, I want to, how do I, okay. Oh, you guys are all muted now. Did I mute you? Unmute. I want to unmute you. Oh, all right, whatever. Okay. So you see, so basically, let's say we wanted to add. Oh, come on. Pictures in the wrong place. Okay. Let's say we wanted to add 1 and 1, 0, which is 2 and 2. So the question is, where would the 0 go and where would the 1 go? So it's a little bit complicated to think about it. With the 1 is not going to go here. You might think the 1 is going to go here, 1, 0. Can you see my pointer? Yeah.
Yeah.
Yeah. Okay. So it's not going to be like that. It's actually going to be the 1 is going to be here, and the 0 will be here, because this is the 0th byte. So if it's 1, 0, this is the 0. This is the 0, and this is the 1. So the 0 is going to go in from the 2. Let's say I'm adding 2 and 2, and I'm going to get 4. So I'm going to get a 0 in here and a 0 in here. I'm going to get, this is going to, the carry in will be 0, the invert will be 0, and I'll get out here a 0, and the carry out will also be a 0. So the 0 will go to a 0. What about the 1, 1? So I'll have a 0 coming in here, and a 1 and a 1, and in here it'll add together the 0 and the 1 and the 1, and it'll get 2. It'll get 1, 0. The 0 will go out here, and the 1 will come out here. Now this one will go into the next one, which you don't see here, but that, ALU number, well, this was 0, 1, 2. ALU number 2, it's going to get the 1 and a bunch of zeros on the other A entrances. Because remember, it's not 1, 0, it's 0, 0, 0, 0, a whole lot of zeros, 1, 0. So all these other 32 A's and B's are all zeros. So it's going to be 2 zeros. On the third one, it's going to be 2 zeros plus the 1 from here. And that's going to add up to 1. And the 1 is going to go out here, and the carry out will be 0. And that will just be a whole lot of zeros. So we'll actually get all the zeros that we wanted, plus we're going to have a 1 and then 2 zeros. So that'll be 4. So it's going to work. That's the idea. I hope that's clear. Now we'll go on to the register file. The register file is the black box, at the moment it's a black box, that allows us to read and write data to all the registers. Remember that there are 36 registers. Wait a second. Yeah, okay. I want to move this. There are 32 registers. Come on, move that. All right, I'm getting a new computer, hopefully soon. I ordered it. Anyway, this is the register file. It allows me access to the 32 registers. Now, we can actually simultaneously read from 2 registers and write to 1 register. So at the same time as I'm reading, I can write. If we have 5 bits over here. When you see this angled line here on the entrance, actually we saw this already in the 32. That means that even though we wrote 1 black line there, it's actually 5 lines. So that's what that slash and the 5 means. So there's 5 lines coming into this register, to this file register. It's a bad name, register file. It should really be called like register reader, but it reads the registers for me. But all inside this box are all 32 registers. And what I do is I put over here 5 bits, which of course is enough bits to specify which register I want, and another 5 bits to specify another register that I want. And those are the 2 registers that I want to read from. So if I tell it I want to read, what's going to come out on RD or RD1 and RD2? Well, if you notice, it says 32 bits. So I'm going to give it 5 bits, and I'm going to get out the 32 bits, which is the content of that register. that I wrote in RA1. And the contents of that register I wrote in RA2 is going to come out on these 32 bits. So I'm going to get the answer to my question, what's in, I want to read these two registers. What does this button do? Anyway, is that clear? Somebody? I don't see anybody.
There's something I'm trying to figure out. Why is it that you're reading in two registers? So you read in two registers, and then you understand, like you are outputted what is in the contents of both of them?
That's right. That's right.
Why is it two? Shouldn't you read one and get one back?
No, because let's say I'm doing an add, and I'm adding two registers. Well, I've got to know what's in those two registers before I can add them together, right? In my add command, I wrote the name of a register and the name of another register, but I don't want to add I don't want to add the number of the registers together. If I wanted to, I said, let's say I give register 3 and register 4. I don't want to add 3 and 4 and get 7. I want to add the contents of register 3 and the contents of register 4, whatever those may be. In order to do that, I need to read two registers. So I'm going to stick in 3 on this line and 4 on this line and get out the contents of those two registers here so that my add will then work. That's what's going on here. And similarly, I'm going to need to write the result in a third register. So I'm going to put that WA is write address. I'm going to put that on these 5 lines here. Let's say I want to write it to register 12. So I'm going to put 12 on these 5 lines, these 5 bits. And, well, actually, yeah. And then the result of I'm not going to do this at the same moment because it's going to be after I take these two numbers and I put them through some kind of ALU over here. Let's say I have an ALU. I'm going to add them together. And then I'm going to put the result on this WD line, write data. And I'm going to tell it I want to write it to register number 12. So these two 32 bits will combine together into a new 32-bit number, and that will go into the write data. There's an additional line here which is not drawn in this picture, which is a control bit. And if it's 1, then it enables me to write to the register file. To the registers. If it's not 1, if it's 0, then it sort of like disables this whole thing for the perspective of writing. It still can read, but it prevents me from overwriting when I'm not interested in writing. It prevents me from writing when I don't want to write. I set the control bit to 0. That's all I'm explaining on this page. Now before I can go on, I need to explain that there's something called a binary decoder. What is a binary decoder? It has n bits of input and n squared bits of output. So in other words, it's got, let's say if n is 2, then it has 2 bits of input. And how much output? 4. What's the point? The point is basically it's like a switch. I choose which line of the 4 that are coming out I want to be lit up. I want to be 1. If I write 0, 0, then it means that the first bit will be lit up and the other will be all 0. So here's another example. Assume let's say I have 5 input lines. How many output lines would I have?
32.
32. If I have 5 input lines, that means I have 32 possible. I have 2 to the 30 to the 5th, which is 32. 32 possible output lines. And let's say I set it to those 5 bits of input I set to 10, 10, 10, which has the value 21. I think it does. Yeah. 16 and 4 is 20, 21. So what means is that line number 21 will be turned on and all other lines will be turned off. There'll be a 1 on line 21 and everything else will be 0. If the enable line there's also an enable line on a binary decoder, which can be set to 0. And if it's set to 0, then nothing will be lit. No matter what number I put on the input lines, none of the bits will be lit up. Furthermore, you could theoretically have an inverted binary decoder, although we're not going to see that in use in this course, but you could have theoretically an inverted binary decoder, which would mean that if I lit up 21 on the entrance, then which lines would be lit up? Every line would be lit up except 21. And 21 would be 0. So that's called a binary decoder. Now let's go to the next slide. And here we see already more what looks like the ALU, or well, actually, we're not actually the ALU, but we're just showing you how this is the internal working side. This is the internal workings of the register file. What we looked at over here was the black box. We didn't explain how it works. Now we're going to look at the same black box, but we're going to look what's going, and that's no longer black. It's going to be clear, and we're going to see through it, and this is what's going on inside it. These are the same register. This is the same right register. I mean, they're drawn a little bit here. I drew all the arrows on the left. Here, they're not all on the left. The two reads are here and here, and the output is here and here. That's why the read data 1, read data 2. This is read register. This is the 5 bits that tell me which register I want to read, and this is the result of that read. This is the 5 bits that tell me which register or the other register I want to read, and the result of that bit. This is the read. This is the write register. This tells me these are the 5 bits that tell me which register I want to write to, and this is the write data. This is the data I want to write to. And this is register write. This is the, remember I told you there's an enable bit, enable line. If this register write is set to 0, then I won't be writing. Then this will be turned off. If I set it to 1, then I'll write something. So in other words, if I set this to 0, then all of these will be off. So let's look at this write first, how it works. So we have this decoder, and we said that if I, let's say, write 21 over here, then only one of these lines will be lit. Which one? Line 21. Now, what is the purpose of these lines here? Well, let's look where they go. They go over here to the register, to the actual register. And the register has on it an enable line. And this enable line means enable for write. Allow this register to be written over. So if you can see, if everything is 0 except for 1, then I won't be writing on any of these except for 1. Now, except for that one that I've lit over here. And if this is 0, then they're all 0, then I won't be writing to any of these. Question? You guys should. I don't hear you if you're asking a question. Anyway, if you're not asking a question, put your microphone on mute. But if there is a question, actually, now's a good time to ask a question. Somebody ask a question just for the sake of asking a question. No?
Yeah, I came a bit late. I just found out about this. Can you give a quick summary to what's going on?
Yeah. What's going on? But I hear some background noise. What's going on is I'm explaining the inner workings of the register file, which is how to read from the registers into wherever I want. I want to read. Let's say I want to do an add command, and I need to read 2 registers to get those results of those registers, so that I can add them. So this is like the machine. This is the hardware that actually enables me to read that register, so that I can add it together with another register, with the contents of another register. These 0 to 31 are the 32 registers in the computer, and I want to choose one of them and choose 2 of them actually, and let the output go on these read data at 1 and read data 2. So let's see how this goes. So, well, actually, we're in the middle of talking about writing. I can also write to a register. So this allows me to choose based on these 5 bits. I light up one of these lines, and that line means that this, let's say if I chose this register 30, then now the data that I put on this D line will be written to that register. So what data is on this D line? Well, if you notice there's a /32 here, that means this one single line is actually 32 lines, and it's the write data. It's the data that I want to write to the register, if it's a write command. So it's a write command. I want to write 32 bits. Now, where do I send these 32 bits? Basically, since we're building hardware, we have to enable you to put it anywhere that you should choose. So that means I need to make a highway going to every single register. So this 32 bits is going to divide up and go to this register and every single 32 registers. So it's going to be 32 lines of 32 lines each. As this line here is 32 lines. This line here is 32 lines, and there's 32 of them, which are all the same data. All the same data, whatever is on this line is going to be like split up and sent simultaneously to all registers. So all registers are getting the data that I want to write. But not all of them will actually. Yeah, go ahead.
How does it know how to split it up into the different registers?
So think of it, I mean, I don't know if you ever like did any wiring in your life, but you know how you can like have a connector and you can put 2 wires on one side and 1 wire on the other side?
Okay.
That's exactly what this is. This is just physically connected. You build 32 wires here, and then you tap them in. You splice them into these 32 lines that are running along here. You actually have 32 lines here, and 32 lines here, and this is what they tap into those lines. You got it?
Oh, each one's getting all 32 lines.
Yes.
Oh, okay, fine.
There's 32 lines running down this row, and all of those 32 lines are connected to these 32 lines and to these 32 lines. So like, it's as though I have a light bulb here, a light bulb here, a light bulb here, a light bulb here. I have 2 lines coming in, and those 2 lines I split up, so all these light bulbs are going to get lit. That would be like a mashal, you know. If these were light bulbs and I wanted to light them up, I would put 2 lines here, plus and minus, and then I would have to split them so that they get to every single light bulb. I'd have a lot of connectors. So actually, there's a little connector. Sometimes it's drawn with a circle here. Actually, we see that in this picture. We see in one of the pictures we saw. Yeah, see here. See this circle there? That means that means that at this point
it's just being replicated in 2 points.
What?
It means it's just being copied in 2 directions.
Exactly. It means at this point, that line is actually forking. It's going in 2 different directions. That same energy, that same chashmal. You can imagine this. If this A was actually 32 lines, then there'd be 32 lines going this way, and another 32 lines going this way, and 32, and they'd all have the same data, whatever was on that. So that's what's going on in this picture. That's the way we build things in hardware. We build it so that like it's like we build a highway, and then actually it's a little bit it's not exactly like a highway because the highway is like 1 car going on it. Here we send a car to every single register with all the data, and then we use this decoder to light up just one of these enable bits. So even though the data is getting everywhere, most of the data is frustrated. It's just hitting this data, it's hitting the register, and the register is saying, I'm ignoring you, I'm ignoring you, I'm ignoring you, but this one has the E lit up, it's enabled, oh, he lets the data come in and write to it. So that's how we select which register to write to. Is that clear? Wait, somebody put off their microphone, I hear some background noise. Okay, background noise, please. Who is it? I don't know. Menachem, I think. Here. No. Ellie. Anyway, let's continue. What about the right side here? So we see also 30. This is the read from that register. And again, all the contents of that register is like permanently connected to this 32 bits, to these 32 lines. And these 32 lines go 2 places. They go to this multiplexer and to this multiplexer. Why is that? Because it could be that on this one I want to read register number 0, and on this one I read register number 31. Who knows? I've got to have the ability to read whatever register I want on this line and whatever register I want on this line. So therefore, every register has to be physically connected to this multiplexer. And there's all 32 lines. So I'm going to have 32 lines coming into here, and another 32 in here, and another 32. I'm going to have 32 times 32 lines coming in over here. What's going to go out on this single 32 lines here? Of those 32, I'm going to choose 1 based on the 5 bits that come in over here. Question? I really actually need questions because unless I muted you, you can't ask.
I have a highly theoretical one, but are there certain, like, each register can connect either to read data 1 or read data 2. So is it more efficient, for example, for register 0 to go to the read data number 1 as opposed to read data 2? Or is there, it seems there's no difference because
yeah, really there
electricity
should be
is
no
very
difference.
fast.
There's no difference. There's actually no difference at all. Even if it's slightly faster, we're going to still have a certain clock cycle, so it's not going to matter.
Okay.
There's no difference. But your question is good because it just reinforces what I'm saying, that I can read from any register anything I want, and therefore, in order to do that, I need all these lines. I need lots and lots of lines. They didn't even draw them all here because it'd be too complicated. They just draw dot dot dot. But you'd have like millions of lines here, and each one you'd have 32 of these lines, 32 of these arrows, going twice. So you'd have 32 times 32 plus another times 2, another 32 times 32. So each of those registers. Now you can see that if I had a 64-bit architecture, it would be even more complicated, much more lines. It would be more expensive, many more lines, and slower, a little bit slower. That's why for years they didn't go to 64-bit. Because like they thought, who needs that? And the cost is prohibitive. But as prices came down, they did it. But just understand that it's physically larger. You're going to have to build it physically larger because you have to have space for all these registers and space for all these lines. And you have to have a bigger multiplexer. A multiplexer, remember, it allows me to choose. I give it 5 bits, and it lets me choose which one of these lines goes through to the other side. That's what a multiplexer does. Did you guys learn multiplexer in?
Yes.
Yes, you learned about it. Good.
Oh, we also learned about decoders, but
Good. Okay. Now, I don't know why I don't. The two output lines, with each containing 32 lines, represent 32 bits of a register, and they can be connected to the input lines of the ALU we previously described. I don't have a picture of that, but in other words, these two outputs, these are 32 bits. Those are our registers that we've read. We can go back up here and connect it to this A can be one of those registers, and this B can be the other one of these registers. And then all of a sudden, we can see that we can have the ability to choose a register, let the values go into the ALU, and get the result of the addition. So we've already seen basically enough to understand how to do add. And this is like this should be like a I don't know, a eureka moment. You're sort of understanding now the basic hardware of how a computer can be worked. Okay, so now we're on to a new section.
What was ALU?
Arithmetic logic unit. I think you weren't there for when we discussed this, but it's this thing which basically knows how to add 2 registers, put them through all of this, and get the result, which can be add or minus or and.
And the result you can write back into another register using the other thing?
Yeah, I could take this result and wrap it around and bring it over to here to this write data line, and then write it to a register.
Okay, thank you.
So we have like the physical hardware. We already understand how to build with multiplexers, a decoder. I mean, we didn't, and the register we know how to make, right? And the register just flip-flops, and it has these 32 bits is nothing really. It's just actually directly connected to each bit of the register. Each bit of the register has a physical wire coming out and going here. I mean, you could, if these things were large enough, you could actually build it with wires. Nowadays they print it on a board, but the wires are just printed on the board, flat. Okay. Now we have a what is it? So this is like a general description of the memory. As far as I recall, we're not really going to explain memory so much, but this is all the data memory. And wait, let me just see. Yeah. This is all the data memory. We give it an address. We say like 32 bits here. We say, I want memory location 100. That's what's written on these 32 bits. And then we say, I want to do, we light here a 1, and we say, I want to read. And then out here comes the contents of that address, or whatever is in that memory. Now we're talking about memory, not registers. We're talking about the whole arba gigabytes. So right, we just have 32 bits saying we want this location. We go to that location. By giving that address, it goes through some kind of like a multiplexer or something, and chooses that one memory, and that data comes out. That's the write, and if that's the read. And if we want to do write, we give it the address, and then we have to look here at the write data. That's the 32 bits that we want to write at this address space, and then that will get written. Right, and that's we have to light up the write bit. If we don't light up the write bit, then we're not allowed to write the data. So for a store word, this will be 1. For a load word, this will be 0. We're just reading on a load bit. That's the memory. Did I explain anything here? Memory is accessed by passing the address location 32-bit input. If the read is enabled, then the contents of that location is sent along the read output. If write is enabled, then the data from the write data is written to the location specified by the address. Okay, I said that. Simultaneous read and write. Note, read and write cannot be simultaneously enabled. In other words, I can't say also write and also read, which is not true of the RF, of the register file. I can have this lit and also read. I can read and write at the same time. Now the question comes up, well, what are you reading? Are you reading what you wrote, or are you reading what was there beforehand? So it's a good question. I have to think about it. It has to do with, we're going to talk about later in the course. It has to do with exactly the latency of the electrical signal. But anyway, that's the idea. So this though, you have to, it's only one or the other. You can't have both read and write. Code memory is not written to during the program run. Okay, so let's think about this. There's the data memory of the memory. This picture here describes all the memory. Some of it is for the code, and some of it is for our arrays. The code being the program. So code memory is not written to during the program run. You don't ever tell your program to rewrite the program while it's running. You might tell it to rewrite a certain. Rewrite a certain data. Certain data in an array. Go to an array, but you won't tell it to change the encoding of this command, of the next command that I'm about to do. You don't write to the actual program code when you're running the program. So code memory is not written to during program run. So this data is built without the write enable or the write data lines. So actually you can use, if you know that you're going to use a certain section of the data always for code, then you don't need to have the extra overhead. You don't need to have the extra lines of the extra physical lines of the write data lines and the enable. You can use a slightly cheaper memory. Now, why can RF be read and written to simultaneously, but memory is only one or the other? Well, the answer is we need to accomplish both actions in one cycle. In other words, the register, there'll be times when we need in one moment to also write and also read. Whereas we're not going to have that need with data. First of all, we have that need. And secondly, registers are fast memory. They can be read and written to faster, so we can do both operations in one cycle. Since they work very fast, it's the data. It takes a long time to choose. There's many lines if you think about it. It's very big, the data. So there's a lot more electricity, a lot more length of lines it has to travel. So to get the data will take long. If we would allow you to read and write, it would take longer, and we'd have to slow down the cycles of the computer. There are a lot more memory locations, so looking up an address takes longer. In other words, physically, the wire has to travel further distance. The cars, the electricity has to travel further on those wires, so it's slower. And we're talking, millions of a second, but it's still slower than the registers. That's why we say registers are very fast. Okay. Now, how are commands executed? Single cycle. Now we're going deeper into this question of how the computer works. On any given command, the program counter contains the memory location of the code to be executed. Right, it points to some line of code. Between each clock tick, which we call a cycle, several actions take place. The first action is called fetch. So we're gonna, I don't know if you have to remember these names, but this is the classic name, fetch. First thing is fetch. The command is loaded. What does fetch do? Command is loaded from the code memory and the PC is incremented by 4. So two things go on during the fetch phase. We load the command from the code memory. Now we stick it into, kind of like we stick it into a register. We copy it from the memory that we just talked about over here in this picture, and we get it into the CPU, into the actual hardware. The next slide shows how the hardware, which does the fetch, is built. So let's go to the next slide. So here we go. The PC is a register. It contains like a value. Like, for example, remember we said it's a register? It's a register PC. But you can't access it. It's just sitting there. It's a register that's just in the architecture. And if the PC is, let's say, 100, then 100 goes in here to read address. And this is the memory. This is a box like the memory we saw. And location 100 will come running out of this line. And now we've got it. We've got whatever is at location 100, which is the code, the line of code, the 4 bytes of my add command or my load word command, whatever the command is, comes out here. But also the PC, not only do I send it here, I also send it up here to, this is a full adder. I send it to an adder with the number 4 hard-coded or built in. In other words, I have 4 bits. I have a, 4 is 100 lit up over here permanently. And that PC, let's say it was 100, it's immediately going to go here, add 4, it'll be 104. It's going to come back through this line and be rewritten into the register, and now PC is 104. So you see, in one step, we did this. We also incremented the PC and also read from the memory the instruction that we want to read. Cool. Question? Somebody ask a question. I need to know that you guys are out there.
We're here. We're here.
Is there nothing not clear about what I said, or you want me to repeat something? No? Okay. So that's this section.
Can you just say in short what's happening here?
Yes, this is called the fetch. And what fetch means is I go to the code. Remember, if I wrote 10 lines of code, so I've got 10 lines of 4 bytes each that does, my loop or whatever it does. It goes through my array. It's 10 lines of code, and it's sitting somewhere in memory. In order for my computer to run that line, it has to know what the line is. In order for it to know what the line is, it has to go to memory and copy it and grab that information, those 1s and 0s of that first line and second line. So the PC is telling us where that line, my first line of my code is. It goes into this address, it grabs that address, and I get the instruction out here, whatever is at that location, which is my line of code. And then the PC increments, and the next time I get the next command, and the next time the next command. Each time the PC is going up by 4, and each time I'm using the memory hardware to get out the command I want. That's what we're seeing here. The next stage is called decode. Remember, we are still within the same clock cycle. So we're still, the clock hasn't changed. It's all still within 1 millisecond, This stage, it's just the next part of it's the next section, next thing we have to do. This stage includes deciphering, which is in Hebrew pinuach, of the command. We have to figure out what the command is. Reading the registers from the RF. Depending on the command, we may need to access up to 3 registers. So this stage includes figuring out what the command is and reading the registers from the RF. Depending, I should change this comma. And reading the registers from the RF. Depending on the command, we may need to access up to 3 registers, right? If it's an add command, we need to do 3 registers. If it's a load word command, it's just 2 registers. But either way, we need to get something from the registers. Actually, is there a command that doesn't use a register? Can anybody think of a command that doesn't use a register at all? We learned a command that doesn't use a register at all. No. I'm waiting. I can wait all day.
Load address.
No, load address has 2 registers. But you have to say, load address. LA. LA is a pseudo command, and the translation of it, I'm thinking, is going to have a register in it. But
What about a jump?
oh, jump. That's what I was looking for. A regular jump, an unconditional jump, is just the opcode and where to jump to. There's no registers involved. Just the actual memory location where to jump to.
Don't you load that? Don't you load that like location where you want to jump to from a register?
No. The jump command. Well, when you type in code, when you're programming, you're going to write something like jump label. You're going to have a label like, the end or start of the loop. But that label is really fictitious. The computer doesn't know anything about labels. The simulator will, instead of that label, put in an actual memory location, a number. So a jump, it's actually jump and then a number in binary number. Got it? So
Yeah.
anyways, so a jump command has no registers involved. The next slide is going to show the hardware that does this stage, that does the decode stage. We see that the RS and the RT registers are the read register, and the RD will be the write register. Let's see. The control on the ALU is set to 2 to indicate addition. So let's look at the next picture. Okay. So what do we see here? Okay, so we see the RF, the register file. That's the box in the middle. And we see it has 5 bits coming into the read register 1, and 5 bits coming to read register 2, and 5 bits coming to the write register. And where are those coming from? Well, they're coming from the command. In other words, I took the command. Essentially, I stuck the command into, let's say, a temporary register. So I've got this some other register that this command is sitting in now. That was the pinuach. I grabbed it from the data and I stuck it into a register. Now this register, remember the registers we said are like surgery rooms in a hospital? They've got things already. There's certain place, you stand in a certain location and you're next to the ventilator. You stand to another location, you're next to the anesthesia. They're built in. So when I cut and paste the command into this register, it's got wires connected to it such that the 5 bits after the first 6 bits, the opcode is the first 6 bits, the next 5 bits are RS. Those 5 bits have 5 lines coming out of them directly connected to read register 1. I'm talking about over here. These 5 bits are physically, there's spliced in 5 lines that go right into the read register. Because after all, if this is a read command, then that's what I want. I want to read this one and read this one and add them together and put them here, right? That's what add does. I want to take the 10 and the 11 and add them together and put them in the 9. 10, 11, put them in the 9. So this is a read and this is a read. So that tells the register file what to read. As we learned, we always saw how this works on the inside. So now we do a read, and what's going to come out of here? The contents of register 10 and the contents of register 11. And they're going to go straight to this ALU. And we're going to get 32 bits. This ALU is that ALU that we built before. Remember that ALU? It looked a little different, but it was big and square. And it had lots of little ALU, little adders in them. But here is a big 32-bit. It takes 32 bits, comes out 32 bits. That result of the add comes out of here, goes all the way around here to the right. And that's the right data. That's the data I want to write. Now, where am I going to write that data to? Well, I'm going to write it to 9, to register 9. Well, register 9 is specified here. They're going to be spliced in 5 lines. They're going to come and they're going to be directly connected to the register file here, which is telling it where to write this data to. There's one thing that's not in this picture, which is that the write enable has to be on this thing. Now, if you ask yourself, well, what am I writing to this? Remember I said, like, what's the latency? Is it what? Maybe the first thing gets written? Because remember, before the two numbers even came here, and before I got them out here, and before I added them up, there was something on this line, right? There was something on that line. Either it was all zeros or it was one, who knows, some garbage from before. Maybe that will get written. The answer is yes, it will get written, as long as that enable is on. It will get written, it's true. But it'll immediately get overwritten. By the time we have one clock cycle, we're only going to look, we're going to keep writing to that data until the clock cycle finishes. And at some point or other, the addition of those two numbers will come running through this ALU down here, and we'll overwrite whatever garbage we may have written there. And then the clock cycle will end, and we'll be on a new command, and everything will be frozen again. So that's how we can read and write at the same time, because we read these things, and we're constantly, you got to think like this, we're constantly reading them for the whole. Imagine the clock cycle wouldn't be a millionth of a second, it will be an hour. So for an hour we're reading this data, for an hour the result is coming out here, and for an hour it's being written. So yes, it's simultaneous. In that hour I'm also reading and also writing. I'm writing the result of that addition, and I'm constantly reading it. Is that clear? Is that interesting? That
Yes.
Should be slightly interesting. That's how you can do two things at once, even though one. In other words, it's the Rambam actually talks about this in Moreh Nevuchim. Things can be the cause and the effect without talking about time. In other words, the cause of this line being, let's say, 100 is the result of this being 50 and this being 50. And 50 and 50 is 100. But if it could be constant. It doesn't have, just because this is the cause and this is the result doesn't mean that this happened first. It could be simultaneous. It can't be after, but it could be simultaneous. Right. Okay. Oh, by the way, I was just, if you're, well, anyway, I want to talk about Rambam, but anyway. What is not done in the decode stage? So, actually, what he says like this, I mean, we're all talking in one clock cycle, so stages is a little bit of a funny thing to talk about, because what I was saying before was that in the cycle, that hour-long cycle, eventually the values will be what they're supposed to be. But in the stage that we call decode, the result of the addition is not ready in the decode stage. In other words, what we call the decode is just that I decide that it's an add command, then I read and I put the data here, but I haven't yet got the result here. And I'm not sure if that's very important, but the result is not ready yet. And it has not yet passed to the write line. Fine. But it's eventually it will in this cycle, because it's a single cycle we're talking about. Neither have we read the function field to know what ALU command to do. In other words, over here, we have not even checked what this function is. So we don't know if it's, remember, it's 0 over here. We don't know if it's 32 or if it's 43, if it's subtract. We don't know what number is over here. So we essentially, so this ALU control line, these 3 bits, haven't yet been set. So, you know, it may give us a subtract. It'll give us actually whatever 0 is. If you remember, according to the picture, 0 should be what? Can anyone remember? I remember. 0 is and. So if these are not set, let's say they're 0. I mean, actually, it could be theoretically some old value. But let's say they're 0, then I'll have an and result here, not an add result here. I haven't even checked the function. We also have not yet lit the register write control bit, so the data line into write data has not been written. And as we haven't written anything yet, because we haven't yet said, go ahead and write. Okay, but that's just in the stage. We're going to write it. Now, that was an add. So we basically understood how the add works without getting into the details of when this is going to be. That's going to be a different cycle. Now, that's going to be a different phase, sorry. Same cycle. There'll be a different stage. But in the same stage, we might have gotten a different command. It might have been a load word command. And remember, we're in the point where we're mifaneach. We are deciphering what the command is. So how is the load executed? Assume we have this command, load W 8 109. This means that RS is 9, RT is 8. RS, the value 9, goes to the read register 1, and its content comes out of the read line. So I think I have a picture of this. Yeah. So look, it says RS. Notice here there's nothing written on the register 2. Register 2 has no line coming in. Obviously there's a line there, but we're not interested in it because we're not going to read from it over here either. It's the same hardware. There is a line coming here, but we're going to tell it to ignore that line. I mean, this picture is not 100% accurate. It's showing you conceptually what's going on, but really there's physically a line connecting this to this, just like we saw before, and there's physically a line connecting here, connecting something to here. But what we're interested in is that the RS is the 9 here, and it's going to this register, and therefore the contents of register 9 is coming out over here. And that's it. Now, what is that 9? Let's go and back and look at that. What is that 9? The 9 is the pointer. What do we want to do with that 9? We need to take that pointer and go into the data and get that what's at the location of that pointer. But we also need to get that location and then add 100 to it. We don't want to go to location number 9. Whatever, register 9 has, let's say, the value 50. We don't want to go to data location 50. We want to go to data location 50 plus 100, 150. So let's see how this is going to do that for us. So look, the 9 comes over here, and the 50 comes out on these lines here. That's what's supposed to, right? It read that content of that register. This is the register file. And the 50 came out over here into the ALU. Well, what's going over here? So look at this. The offset, see it says offset here? And it says 16 bits. The 16 bits of the offset, this is the instruction. Let's see, what is this? Let's look at this now. This is a little bit confusing here. Because this is the 32 bits of the instruction. That means, just like I had before, I have these, oh, my battery is running low. Let me go to this one. Go over here. So wait, so sorry, I'm talking. I gotta talk this like this, but I'm talking. So wait, let's go back here. This is this register, right? This has got the whole command in it. The whole hurrah, the whole, like the add. But in this case, it's going to have the load word or the store word. And the 16 bits on the right is the offset. So let's go back to this picture. So here's the instruction. Here's those 32 bits. And what we're writing over here is that this is 32 bits coming in here. And 5 of them branch off to over here. 5 of them branch off to over here. Obviously, another 5 of them branch off to over here. We're gonna actually no. I take it back. 5 of them branch off to over here. 5 of them branch off over here. The opcode has already been taken care of, so we don't have that in this picture. But the opcode, the 6 bits of the opcode are, let's say, somewhere else. So that's 5, and 5 is 10, and 6 is 16 for the opcode. The other 16 branch off over here and go here. So that's why it says 16 over here. It's 16 of those 32 that are over here. So that's the offset. Now the offset comes in here. It's 32. It's 60 bits. It gets sign extended. That's it says sign extended, and it comes out of this little circle as 32 bits. We sign extended it. Now it can go into the ALU along with whatever value of the pointer that we had over here, and those two numbers will be added together, and we'll get a 32-bit number, which is the real address we want. Because we didn't want just the pointer, we wanted the pointer plus the offset. And that will go into the data memory over here, 32 bits, and we'll tell it, okay, I'm interested in that location. And that location will have a memory read lit, and the memory write will be off. And the output of this read data really should be read data. The data that has been read will now be coming down this line and coming over here and into the right register file. And then it's going to look at what's written over here. This is the second 5 bits. That's in our command, for example, that's 8. That's where we want to write to. That's this 8. So this 8 is going to be sitting over here, just like he wrote, 8. And we're going to write the result of that data read into the register file at location number 8. So now we've explained how the load word works. Any questions? clarifications? Somebody wants
Yeah,
to say
so
the
did this essentially work through logic gates, or
which? I mean,
like this circuit?
everything is a logic gate. I mean, you're saying, well, these are just physical lines. There's no logic here. There's just.
So they don't actually represent logic gates here. Here would be different.
Well, or no, we're not doing anything. I mean, inside of this thing, there's a multiplexer, and right, and in order to make a multiplexer, don't you need logic gates? So there's some logic
Wait,
gates in
RF
here.
is
What?
RF is the multiplexer. I thought the RF is the registers.
Yeah, the RF is the registers. But look, let's. Oh, sorry. The RF is the registers. This is a hard class to teach this way because this is like complicated stuff. This is the RF? Isn't this a multiplexer?
Oh, yes. So you're saying there's in the RF itself is its own actual thing, which inside there's both registers and multiplexers.
Yes. This whole picture is the RF. Remember, this is the same.
And a decoder.
And a decoder, right. This is the RF in a black box view with the lines in and lines out. And this is the internal workings of the RF. And it's got a multiplexer there, and it's got a decoder there, both of which require logic gates. And these are flip-flops. So there's definitely logic gates. And then when we're looking over here, we're looking like in a view that's much more high up. We're just looking at that as a black box.
It's more like zoomed out.
Yeah, we're zoomed out. And this is the ALU, obviously has logic gates in it. The data memory, we didn't, I don't know why. I mean, I'm following the lead of Shmuel Weinman. He didn't explain exactly the inner workings of the data memory, but it's got to have a lot of lines. But there's also got to be some kind of multiplexing going on in here. So I got 32 bits and I'm reading something. So there is logic gates, but these lines that you see are just physical. But no, I mean, yes, what you're saying is actually an incredibly important point, which is that this division of the instruction, of taking the instruction and setting the lines to go in different places, that is done without logic gates. That's just done like, an electrician. It's just how you divide up the wires. That's just how you just took 16 of the lines and put them down here from the instruction. The last 6, the least significant bits, the least significant 16 bits are just connected directly here. If that's what you meant, then that's an excellent point. But there is certainly no logic in that. All right, I guess it's actually, I'm trying to think if we should continue. I was planning on teaching with just by putting videos up on YouTube and letting you guys write comments on the bottom if you have questions. But maybe, is this, do you prefer doing it this way?
This way is good, yeah, because that way we could ask the questions live and you can answer them live. And yeah,
Right.
It's more like a real classroom.
It's more like a real classroom.
Yeah. Just is it possible next time maybe I didn't have that much of a warning about when the class was going to be? Are we able to just have a little bit?
Yeah, well,
more
this was
of
a last
warning
minute
beforehand?
thing. Say it again.
Just because, yeah, like I only found out 10 minutes ago that we have a class now. I didn't see
Exactly.
the email.
I know. I'm sorry.
Also,
I will try to. This is my first time using the Zoom because I was doing everything with YouTube.
Also, it looks like you recorded the class.
Yeah, so I'm gonna try to post it.
Okay, fine. Yeah, on Moodle or your YouTube account.
I think I'll post it on YouTube and then I'll put a link in Moodle.
Okay, that's great.
But I have already. If you're interested in Hebrew, I've already posted a bunch of things in Hebrew.
I'll wait for the.
Can you post the Zoom link next time to Moodle?
Oh yeah, that works better also.
Yeah, I'll
some of
do
the
that
other teachers
also.
have done
Oh,
that.
not just email. You're saying. Now I have a question.
Yeah.
Do I have to send you a link, like a new link for each class?
I think so, yeah. But I think the other teachers have done, they put it in Moodle under their folder, and then we just go to the folder of the teacher, and we click on whatever's there at the time, and they delete the previous ones.
And they delete the previous one. So I've got to go and add it every time I want to teach.
Kind of like the homework.
What?
Kind of like the homework.
Kind of like what the homework?
Yeah, like adding a new one every week.
Exactly. Well, the homework, right? The homework we just add. I can put them all up right in the beginning, and then they just see them. But
Wait,
yeah.
so tomorrow do we have a class at 1:30 then?
Tomorrow, yeah, I guess, yes. Tomorrow, I'll have a class at 1:30. Yeah, okay. Yeah, let's try. I'll try to put up a link for tomorrow. I have to make the link again.
Okay.
All right, so we'll
I have
stop
a
here.
question.
What? Yeah, question.
I have a question about the lab. They cancel the lab?
So the Rakaz of the course says he can't. Says he you cannot run a lab on Zoom. I mean, he's right in a certain respect, which is that you can't check homework really easily. But as far as like instructions on how to do well, I've already given you all the instructions. What I suggest you do is you do all the labs. I'll try to post a video on YouTube on how to do functions, so you can do lab 4. I suggest you do all the labs as much as you can without my help. And however, and if we eventually do have labs somehow where we meet, then it'll be good. And if not, then at least you learn something.
And another question about the homeworks.
Yeah.
How is it gonna be? The homeworks on this.
So I've been trying to get from Shmuel Weinman to send me the homeworks in a Word document so that I can translate them more easily. I have to call him. I called him today and he didn't answer me. So I'm going to try to. I want to get you translated the homework for the theory you're talking about.
Also, this isn't connected to you, but I was just wondering, we've been getting emails from every single professor who's teaching every single course, and it makes it kind of hard to figure out what's relevant for us, which is part of the reason I didn't see the lecture for today till like later, because like I've been getting like 50 emails from a Chalna per day. Is there a way like maybe you can mention that to someone?
Yeah, people, they've already written letters to us to say, please send only to your group.
Oh, okay, fine.
So people have been told that.
We've still been getting it, yeah.
I mean, really, you think you're getting every single one, or you think some people are sending and some people are not?
I mean, it could be some people are not sending me. I've been getting like around 50 emails from a Chalna per day.
That's pretty crazy. Okay. Well,
it just makes it hard. It just makes it like hard to like look for the stuff that are actually relevant. Like I'm saying the class here, like I didn't see it right away because it was mixed in with a lot of other stuff from no reply.
Yeah, I understand. No. This complaint has been registered already a few days ago. The higher ups know about this problem. I don't know why it's still going on. As teachers, we've received an email telling us don't send everybody, just send you a group.
Yeah, I actually received that email too.
What?
Funnily enough, I actually received that email too.
You're a teacher, man.
There might be a bug in the program. Might be that.
It could be.
Yeah.
I think the problem is that it's because all of these forums were all in the same Moodle because it's all the same course. So everyone's posting in their forums, but it doesn't matter. We all still get what everyone's seeing, like whatever's.
But I sent an email today, for example. I selected my group, and then I added everybody in the group to the Decode, to where I sent it to, and I saw the names of 20 people, and I sent it to those 20 people. I don't see why anybody else would get it. I'm not posting a general post to the group. I'm sending it to my students. See if you know somebody who's not in our class. Ask him if he got my email today. I bet you did. I think I did it right. I think it could be done correctly. Anyway, I'll post this. I'm not going to guarantee that I'm going to do this every time in Zoom because it's well, I'll try to do it every time in Zoom, but it's a lot of extra work really for me. But I'll try.
Are you also able to put the links for what we should download, both the Java compiler and the Mars program in Moodle, so we could get the right ones? Like I
actually put
or even a link.
I know your Hebrew is not so good, but but you can just watch even if you don't understand it. I did actually post a tutorial in the lab section
on how to install it.
On how to install it.
So where is it? That's in Moodle?
Yeah.
What's it under?
It's in the lab, not in the not in the lecture, and it's under. You'll see my name. Look for my name. Pretty much towards the top.
Okay. And it's like a video tutorial.
It's a video tutorial. 7-minute video tutorial.
On how to install it in your computer.
Yes.
Okay. Thank you.
Okay, so I'm going to end the call now. Sorry about the last minute notice. I'll try to do it earlier.
Okay, I'll watch the video again later.
Yeah. Stop.
Bye.
What do I have to do? Stop recording there. I should have done that earlier. It won't let me stop recording. Wait. Stop share.